Okay, so we're going to start stoichiometry. And like I mentioned earlier, stoichiometry is basically, we've been learning the pieces of the puzzle like molar mass, how to convert grams to moles, how to balance equations, how to write formulas, and we're putting it all together for this unit. So this is like putting the pieces of the puzzle together. So if you're still struggling with some of those pieces, you might have to go back and revisit those and make sure you understand them, okay? Like I said, it's all math unit. So let's talk about exactly what stoichiometry is to begin with. First of all, it is a proportional relationship between two or more substances in a chemical reaction. That stoichiometry relationship can exist between several things. It can be between moles, grams. It can be between volume, which would be in liters or milliliters most likely. Or it can also be between atoms. And what's cool about it is if you have the balanced equation, you're going to be able to relate any one thing in that equation to anything else in that equation. Okay? It's the study of the amount of substances consumed and produced in chemical reactions. Okay? You must always, write it big, start with the balanced equation. You cannot do stoichiometry without the balanced equation. Okay? So in a nutshell, what stoichiometry is if I have my balanced equation and I go into the lab and I weigh out, let's say, 15 grams of one of the reactants, and I do the reaction or whatever, I can calculate how many grams of the products that I should get. Doesn't mean I will get it, but I can calculate how much I should get. Okay, so that's what stoichiometry is. It's that relationship of one item in the balanced equation to something else. The mole ratio is the basis for all stoichiometry problems. Okay, so the mole ratio always comes from the balanced equation. And I'm sorry if I didn't leave y'all enough room to write. Sorry, I forgot to do that. Okay, the balanced equation gives you the mole relationship. So the coefficients, those big numbers we've been balancing with, are equal to the number of moles. So if I look at this equation, I have nitrogen plus 3 hydrogen molecules yields 2 ammonia molecules. Okay? So that means I have 1 mole of nitrogen molecules, I have 3 moles of hydrogen molecules, and I have 2 moles of ammonia molecules. Okay? So we can use that ratio or that proportion to figure it out. Okay? For instance, how many moles of NH3 are produced from 3 moles of hydrogen? Look at the balanced equation. For every 3 moles of hydrogen, I get 2 moles of ammonia, right? Which is easy if I'm using the moles that are given to me in the equation. Okay? How many moles of hydrogen react with 1 mole of nitrogen? 1 mole of nitrogen is in the equation, right here. Okay? So it's 3. So that's 3. That's just kind of showing you what that mole ratio is. Okay? The mole ratio, it exists between all of those. So you can do a 1 to 3 relationship with nitrogen to hydrogen. You can do a 1 to 2 relationship with nitrogen to ammonia. Okay? All right, and so this is just kind of a equation to show you like this bottom one, just basically a example equation, nothing that's real. So let's do a couple of these, because you have to understand, you really need to understand the mole ratio, because without knowing how to do the mole ratio, you can't do any stoichiometry problem. Every single stoichiometry problem that we're going to do has the mole ratio in there. It's how we go from what is given to what is unknown or what we're looking for. That is how we convert from what we're given to what we need to know. Okay? So this is that same equation that we just used. I'm going to jot it at the top so we don't have to keep referring back to it. So for N2 plus 3H2 yields 2NH3 ammonia. Okay? So this one wants to know how many moles of NH3 are produced from 2.5 moles of nitrogen. Okay? I know, this is like when we did this earlier in the year when we did dimensional analysis. I know you could do this in your head, but we're going to have 2 and 3 step problems coming. So please do it the way I show you, because it will help you as we do multi-step. Most of our problems are not moles to moles, because I don't go into the lab and measure out moles, do I? I measure out grams. Okay? So please just follow through and do the setup that I'm showing you. Okay? So if I have 2.5 moles, I always start with my given of N2. I want to get rid of moles of N2, so where do I put it? On the bottom. So I go to my balanced equation, and there's nothing in front of it, so I assume 1 mole of nitrogen. I am trying to get to what? What is the problem asking me for? How many moles of ammonia? So that is what's going to be on the top. The moles of unknown is always going to be on the top. So I go and I see that I have 2 moles there, so I do 2 moles of ammonia. And then I cross out, and then I cross out. So now, just like when we did dimensional analysis, if there's numbers on the top, I multiply, and I divide by what's on the bottom. Okay? So in this case, I multiply the top, and I get 5 moles of ammonia would be my answer. I'm running out of room, sorry. Any questions so far? Does it seem pretty straightforward? I got the 2 moles from right here.
Where did you get that from?
That's the balanced equation.
So you have to write it out?
Well, yes. We already had it on the page on the previous slide. I just rewrote it. But you cannot do this without a balanced equation. You always have to start with a balanced equation.
Up above?
Yeah. For y'all, it was already on the page. I just brought it over to the slide so we could look at it and refer back to it. Okay. So the next question says 6 moles of hydrogen. So that is our given. So that's what we're going to start with. 6 moles of hydrogen. Just like when we did dimensional analysis, whatever I write down here, that unit, it needs to immediately go down here. I don't know what I just did on this. So I'm going to do, and I go look at the balanced equation, and I have a 3. So I'm going to do 3 moles of hydrogen on the bottom, and still wanting to know moles of NH3. So I still use that 2 from the balanced equation, and I say 2 moles of NH3. Cross out moles of hydrogen, and now I multiply 6 times 2, hit equal, and then divide by 3. I forgot to tell you how to get calculators out, so we'll get one in a second. But if you do that math, it's 4 moles. Okay? Again, I'm stressing this because you need to understand you always start with a balanced equation. So that's what these blanks are right here. Balanced equation. And show your work. Including the units, especially when we're first doing this. Because if you're just putting down numbers and you look back, you don't know why you put those numbers there. But if you put those numbers with a unit, you can kind of see what you did, see the steps you took to get to the answer. Okay? So that is the mole ratio. Okay? I think I have 2 more examples to do before we move on to real stoichiometry. That's just fake stoichiometry. That's just baby stoichiometry. That's just the mole ratio. That's to help you understand the mole ratio. We're going to do real stoichiometry after we understand the mole ratio. Okay? So first thing we always have to do is balance the equation. This next one, example 1, the equation is balanced, so we can just do that. Okay? So we're going to start with this 0.6 moles this time of nitrogen. Again, whatever unit I wrote down, I'm going to put it in the next step on the bottom. And so that was moles of nitrogen, and it wants to know how many moles of ammonia are produced. So we'll put moles of ammonia on the top, and then we go look at our balanced equation, and we get those numbers. So in front of nitrogen is a 1, in front of ammonia is a 2, so it's 1 to 2. And of course, if we do that math, we can do that one in our head. Our answer is 1.20, because we need 3 significant figures, moles of NH3. I heard someone go, yeah, significant figures are still into play. Match your significant figures to the what's given to you. That's what you're going to match it to. Okay? So this next example has the formation of aluminum oxide from aluminum and oxygen. It wants to know how many moles of aluminum are needed to form 2.3 moles of aluminum oxide. Okay, so that's our given. I always try to underline our given. But what do I need to do first? Balance the equation. Anybody want to tell me what those coefficients would be? 4, 3, 2. Thank you. 4, 3, and 2. So now we can proceed. Okay? So again, we start with what's given to us. So we start with the 2.30. So how many sig figs will I need my answer in? 3. So I always kind of jot that down over to the side. And that is moles of aluminum oxide. Okay? And then we put same unit on the bottom because we want to get rid of it, moles of aluminum oxide. And it was asking for how many moles of aluminum are needed. So we're going to do moles of aluminum on the top. So then we go to our balanced equation and get what those numbers should be. So for aluminum oxide, it's a 2 right here. So I put a 2. For aluminum, it's this 4, so it goes right there. Multiply the top, divide by the bottom, and you should get 4.60 moles of aluminum, and that would be our answer. Okay? Any questions on the mole ratio? Okay.